Welcome to our project Infrared Vibration Sensitive LED Drum and Metronome, aka LUDS, Light Up Drum System. We are Group 10 and we consist of four people: Aaron Holloway, electrical engineer in power and renewable energy track, and myself, Ajay Natan, my also electrical engineering in comprehensive track, and Elisha Peterman, also electrical engineering in comprehensive track, and Malcolm Donaldson, who is in photonic science and engineering major. So to begin with our project description, it's a simple snare drum with six reflectance sensors under the skin, which detects the vibration and outputs a visual signal to the LED strip and LCD display. It consists of two modes, uh, the metronome mode and the sensing mode. In metronome mode, the device acts as a musical metronome by flashing the LED strip in a specific rhythm, which is set using the BPM knob. And in sensing mode, the sensor detects the beats each time and flashes to the LED strip. And the display will display the mode and the BPM, which can be modified using the knob.
Here is our task distribution. Aaron Holloway worked on the power supply. Ajay Natanmai did the software design and worked on the MCU and display. Elijah Peterman did the LED array and the user interface. And myself, Malcolm Donaldson, designed the IR sensor array. Here is our goals. Our key goal is that the LUDs should be able to detect the vibration of each strike from any point on the drum. And some of our other core goals are listed below, such as the development of metronome mode and making the LEDs change color. Here are our objectives. Our core objectives were things like making sure the beats are detected by IR sensors, having a UI controlled by knobs and switches, uh, making the power supply operate on both AC adapter and rechargeable battery, and some of our advanced objectives are listed as well. Here are our engineering specifications. Our three key specifications were that the LUDs should allow for a maximum 240 LED flashes per minute while performing in metronome mode, which we were able to achieve. The reflectance sensors must be placed between 0.25 and 3 millimeters below the skin of the drum to detect vibrations at any point on the drum skin, while not detecting the skin while the drum is at rest. We were able to do this while also finding that the optimal range was somewhere between half a millimeter and a full millimeter below the skin. Our final key specification was that the LUDs needed to be designed to operate using both AC adapter and a rechargeable battery for a minimum of 2 hours, which we achieved.
Here we have our project block diagram. To the right is the legend with each teammate and their respective components that they worked on.
This shows the general layout of how the different components sit inside of the drum. The green line indicates where the LED strip will be placed on the inside perimeter of the drum, and the red area indicates where the infrared sensor array will be placed. This figure shows the drum upside down, looking into it from the bottom.
Here we have our power supply design, which makes up the AC adapter, battery, power switch, voltage regulator, and non-inverting amplifier. 12-volt regulated DC power is supplied from the battery or adapter, which is then sent to the power switch. This DC signal is then sent to the voltage regulator and non-inverting amplifier, respectively. The voltage regulator is necessary to step down the voltage to a level of 3.3 volts for the MCU to operate. Next, we have the voltage regulator schematic. It comes in between the two voltage signals and between the input from the MCU. The converter chip used will be a synchronous buck converter named the TPS5632212DR LR. Next is the voltage inverter circuit, which is in between the previous buck boost converter and goes to the VCC of the op amp design. Next is the battery and component selection. The battery utilized for the LUDS device will be the 18650 battery pack from Battery Int. The battery is lithium ion and rated for 6,000 milliamps with a voltage of 12 volts, having an average current consumption of about 2.147 amps, which helps to enable to have battery life of over slightly 2 hours. Next is the power switch component selection. For this device, we'll be using the A40315RNZQ. That is a 3-position 4-pole switch, which is necessary to enable the user to switch between the 2 voltage signals safely and also turn off the device. Next would be the AC adapter component selection. The AC adapter will be a 12-volt 4-amp AC to DC converter made by CoolMC, which also includes a DC connector that allows for loose leads to connect to either future connections.
Here's our optical design. There is an array of 6 infrared reflectance sensors that rest just under the drum skin, all spaced roughly evenly apart from and are formed from an IR LED, which is represented by nodes 1 and 2 on the diagram below, and a phototransistor, which represents nodes 3 and 4, and the drum skin representing the hatch-marked area. The IR light from the LED is reflected into the phototransistor when the drum skin is deformed, and this causes a voltage drop in the output of the phototransistor. The MCU detects this voltage drop and uses it to activate the LEDs. The larger the voltage drop, the closer the drum skin gets to the sensor. The IR LED is connected to the power source by a 33 ohm resistor, which is represented by R1. R1 needs to be at most 100 ohms to allow the sensor to function, and lowering the resistance increases the sensitivity of the sensor. The phototransistor is connected to the power source by a 10 kilo ohm resistor, which is represented by R2, and the output of the sensor, the overall output of the sensor is located between R2 and the transistor, which is represented by node 3. The reflectance okay, sorry, I forgot that I had 2 in a row. 3, 2, 1, cut here. The reflectance sensor component selection. The only real choice was the QRE113s by Onsen. These reflected sensors are analog and can be used to capture varying light levels. They are also both power and cost effective, and are very small, and this means they have a short range but are also fit within the drum very well.
Here we have the overview of the LED design. A 3.3 volt signal comes out of the MCU and is then sent into the non-inverting amplifier, which amplifies that 3.3 volt signal into 12 volts, which then leads into the dimming module. The dimming module controls the color of the LED strip and the flash and fade modes. The output of the dimming module goes to the LED strip, lighting them up at 12 volts. This shows the math behind the design of the non-inverting amplifier. Since the input signal is 3.3 volts and the output signal needs to be 12 volts, a gain of 3.6 is required. The gain of a non-inverting amplifier is equal to 1 plus the ratio of the R1 and R2 resistors. We chose R1 to be 1.6 kilo ohms and R2 to be 1 kilo ohms. This shows the schematic of that non-inverting amplifier circuit. We have 12 volts and negative 12 volts going into the rails of the amplifier. And on the right side, we have the AC sweep of the circuit showing that if we used a pulse width modulator to dim the LEDs, we could vary the frequency all the way up to 10 to 1 megahertz before attenuating the output. This is just the Eagle schematic of that non-inverting op amp you just saw. Next we have the op amplifier component selection. There were two main amplifiers to choose from. One was the TL084CN, the other one was the LM358DR. We went with the TL084CN because it has 4 circuits in case we needed more in the future. It has a very high slew rate, which was the main plus of this one, because a high slew rate is needed to decrease the latency of the drum. Uh, it has a voltage supply range of 10 to 30 volts and a very small offset voltage of 3 millivolts. It is a little bit more expensive than the other one, but they're both very cheap. Here we have the component selection for the dimming module. Both dimmers were pretty similar, but we went with the more expensive dimmer 3CH because it has a full RGB spectrum of programmable colors. This slide shows the two main choices we had for the LED strip. They're both very similar, but one is side emitting and one is forward emitting. We went with the forward emitting because of the way they are placed inside the drum. They are not shining directly into the user's eyes. It's better for health and safety. Here we have the switch component selection. We chose this switch, a toggle switch. It's a single pull double throw rated for 5 amps and 120 volts. It's priced at just under $3 and has a lifetime of 20,000 cycles. This is the switch Eagle schematic. We have some pull down resistors here, 34K ohms, and they're there to reduce the noise. The knobs we went with are these incremental rotary encoders. They use 2-bit quadrature and cost just under $4 and are rated for 30,000 cycles. This schematic shows the filter used for the rotary encoder. It consists of pull-up resistors, pull-down resistors, and filter capacitors to filter out any unnecessary noise.
Here we have the MCU. We chose MSP430FR6989 because it is a programmable in C language, and we have multiple pins to be attached to this MCU from other components. So the switch requires 2 pins, and the knob requires 2 pins, and the LED strip requires 1 pin for the output and the ground pin. And the sensors inside the drum requires 6 pins, 1 pin individually, and each of these pins are connected to the MCU to operate according to the specific functions. And here we have the schematic of the MCU. We have used Code Composer Studio to program the processor. The output voltage of 3.3 will be used to power the other components, and the MCU itself is powered mostly by the device it's connected to, and it also receives power from the battery. The pins connected to the components are taken as inputs and enabled to be initialized to perform as needed. Here we have the user interface display. It's a basic Section X2 display. It's a black on green screen, and it's compatible with MSP430 microcontrollers. It displays 16 characters in each line, and we have the example below right here. So the first line shows the mode as metronome or sensing, and in the second line it displays the BPM in 3-digit values. And we do have some design constraints for the project. To begin with the economic and budget constraints, our project is not funded by sponsorship, so our own group's funding is used for all the components. And for the time, we have 2 semesters allotted, and using this time we have to buy each of the components for the project, and there could be delays such as the PCB and the primary components such as the MCU. And the environmental constraints include it could create waste that could cause pollution and toxicity, which should be avoided. And the health and safety constraints are there, which such as the drums could cause heavy sounds, which should be avoided, and the battery and LEDs could be fused or explode due to overheat, and the manufacturability should be scaled down to be small in size so that it can be moved very simply, and it has to sustain long enough until the showcase of the project.
Okay, next we have the PCB layout. As you can see in the middle, we have the MCU. Towards the bottom right of that, on the bottom plane, actually is the op amp. We have a couple of solder points. To the top, we have all of the switch. On the top, I'm sorry, we have the rotary encoder solder points. To the top left are the switch design. From the left of the MCU are the IR sensors with a couple of extra solder points for any additional sensors that we think should be included in the project. To the bottom left are the solder points for the LCD display. And also to the right of the MCU are the 5-pin header for future programming use. Now, there are many complications pertaining to the PCB. The manufacturer sent the PCB back with parts without parts assembled, which wasn't what the group had intended. Our solution was to send both boards back. However, due to long assembly times, we decided to send one board back to us and leave one with the PCB manufacturer. The lead times for certain components are quite long, so we are waiting to receive said components to microsolder the PCB board ourselves. We plan to finish the design with whichever PCB gets to us faster.
This slide shows the budget we created in Senior Design 1. We were estimating it would cost about $485. The actual amount we spent is closer to $730. This deficit is mostly come from the expedite shipping costs and lead time for the PCB board. This shows the different parts, like the different circuits inside our project. We're undoing the skin of the drum so we can take a look at what's underneath. We're going to look at the 6 sensors that we have set up on breadboards. Here we can see the different resistors we have in parallel to increase sensitivity. You can see the 4 nodes of the sensors. They're placed on a wooden panel that's connected by bolts that we use to raise and lower the sensors to find the ideal distance from the drum head. If you just put a finger or any object in front of those sensors, it will reflect the infrared beam back onto them, and which will tell the MCU to light up the LEDs. All of those sensors are wired through this hole. The LEDs go to this dimmer module that controls the colors. Here we can see the LEDs are wrapped around in the top part of the drum. This is the MCU where pretty much everything is connected. It's the brain of the project. Next, we're going to look at the rotary encoder. Here we go. You can see the solders we've done. The rotary encoder is connected to a filter circuit with those capacitors we talked about earlier and the pull up and pull down resistors. Here we have the strip switch that switches between metronome mode and sensing mode. And here we can see the pull down resistors we have to filter out any noise. This is the LCD display and the circuit that powers it. This is the potentiometer we have that can control the contrast of the LCD display. This is the power switch. It has 3 positions. One position is powered by the wall outlet. The other position is powered by this battery. And the middle position is the off mode. And finally, we're going to take a look at the operational amplifier circuit. The op amp has those 2 resistors. We can see the 1.6K is made by two resistors in series. In the 1K is just one resistor there. Thank you very much. That is the overview of the circuits within the LUDs.
And here is a demonstration of the LUDs in performance mode. We can see that hitting the power switch turns the LUDs on, and now it will react to the drum being hit against the drums. Here's a demonstration of the LUD's ability to change color with the dimmer module, and the different patterns of drumming show how the LEDs are quite responsive. Here we can see an interesting phenomenon that occurred where the LEDs would flash as different colors. This was not initially part of the design, but we decided to put it because we thought it looked striking in performances. And here's just a further demonstration of how the LUDs, how dynamic the LUDs is.
Next, we have the demonstration of the metronome mode. And then now we're transitioning to
Here we have the demonstration of the LCD display. So to begin with, it's starting in measure sensing mode, and it can be switched to metronome using the switch, and it can be switched back to sensing and back to metronome. And the rotary knob can be used to change the BPM. As you can see, it can be changed to a maximum of 240 BPM, and it can be reduced back to a minimum of 15 BPM. And here's our future plans. So the final presentation will be completed along with this today, and the final documentation will be completed before April 25th. And as soon as our PCB arrives, we plan on completing the soldering the components onto it.
This has been Group 10 with the Light Up Drum System, or the LUDs. Thank you for watching. Oh, and cut here.